Going through integration? Sure. And how's that been going?
It's okay, but it's like, should still review it.
Still review it? Sure. Okay. So let's take a look. Integration. Whereabouts did you get into well, where are you starting to want to review?
Um, could we go finding the area under the curve?
Yeah, absolutely. Area under curve? Sure. So what I'll do for that is bring up my notes on that and we can have a look. So let's see, definite integrals. Cool. So finding area under a curve is in basic part, what you're doing is you're finding what's known as the signed area, which basically means that any area like above the x-axis is considered positive. So like for instance, all this here would be considered positive area, and all this would be considered negative area. So that's one thing worth considering. The other is that that's only in the case of signed area, or basically whenever you're solving a definite integral. Definite integrals by their nature do exactly that. They figure out whether it's below or above, they compensate for positive and negatives. In a lot of cases though, you don't actually want it to be considered signed, you want all of it to be considered positive. And so what you do in that sort of circumstance is you start by splitting the integral up into two separate sections. So basically, if you consider that exact same graph, you can see there's clearly a positive section, clearly a negative section. The negative section goes from 1 to 2, the positive section goes from 2 to 4. And so all that means is you split it up into two individual sections. The function maintains the exact same as it always has, but now you've got different terminals. From here, there's a couple of ways you can handle this negative area. The first is to literally just slap a negative sign on it, and the second is to just flip the direction of the terminals. Instead of doing 1 and then 2, you do 2 and then 1. That's pretty much it for fundamentals on how you go about handling those scenarios. From then on, it's just how do you do definite integral? Do you need a refresher on doing definite integrals?
Yes, please.
Sure. So first step of doing definite integrals is always to antidiff. So you take your function, which in this case is x squared minus 4, and you antidiff that. This is the power function antidiff, so you raise the power up by 1 and you divide by that raised power. This is a constant, so all you do is slap an x on it, and all antidiffs, of course, are going to come with some plus c. In the case of definite integrals, though, we don't really care to write that plus c. And then from there, once you have that capital F of x, that antidiffed function, all you do is you look at your terminals and you sub in the top one and then subtract the bottom one. So basically, if we're doing this definite integral here from 1 to 2, you do capital F of 2 minus capital F of 1. That's this bit here. Or if you're doing this bit, it's capital F of 4 minus capital F of 2. The top minus the bottom. Fair enough?
Yep.
Sweet. And then, yeah, anything on the outside just stays on the outside. So it's a negative of this integral, the negative sign stays at the front. Otherwise, yeah, that's pretty much it. There's a whole bunch of these here, but they don't really pertain too much to what we're talking about. Mainly this one, the whole idea of reversing the terminals, flipping things to being negative. But otherwise, yeah. So, is there any place in particular you want to start? I'm pretty sure 11F is a little bit further than... Yeah, because 11E also does it. Whereabouts would you like to start?
We can start here.
Start here is fine. Cool. So 11A, pretty sure is only doing signed area. It's, yeah, okay. It's not even going to say the word signed area. It's just going to say do some definite integrals, which does mean you'd probably want to have a look at the properties of the integral again, but maybe we'll have a look at that when we get up to it. So let's see. Yeah, I'll do a screen grab of this whole, well, maybe the first part of this summary. I'll put that in the chat. And then also for reference, I'll grab the anti-diff table as well, so you can refer to that to do the first stage, which is your antidiff of the function. All right, that's those two. Yeah, that's about it. So we'll start pretty chill, starting off with just 1A there. Do you want to try them yourself, or do you want to work through them live?
I can try it.
Sounds good to me.
I got 7/3.
7/3 is correct. Yeah, nice and simple. A lot of these are going to be similar levels of difficulty. You're going to have like fractional values, you're going to have like squared things. Is there anything in question 1 that's worth having a look at in any more detail?
I think it's okay.
That's okay. Nice. Question 2 also looks quite similar to me as well, except now you've got like roots and negative indexes. Any of those worth doing?
I think I'm okay with these. It's more like just finding the area under the curve.
Yeah, okay, sure. Fair enough. Let's move straight to that then. Okay. Let's see. What's question 1 telling us? Sketch the graph, find the exact area. Okay, so exact area, if you're looking for keyword exact, that's where you have to consider all the negative area is now considered positive area. Yeah, so we'll start 1A on this one. First thing you want to do, obviously, is actually sketch it. That way you can see where's positive and where's negative area, and that becomes a lot easier to handle from there. Although in some cases you don't really need to. Like if you can picture what 3x squared plus 2 looks like, you can pretty quickly figure out that it's only going to be positive area in that case, but drawing a picture always helps. Do you want to try that yourself or live together?
Could we do it together?
Certainly. Let me just pull up the phone again. Okay, so first things first would be to sketch that function. How do we sketch 3x squared plus 2?
Would it be a parabola?
Sure will, yeah. What are the key features that we could immediately figure out?
The y-intercept, which is 2.
Yep, y-intercept is 2. That also happens to be another key feature, which is,
The turning point.
yeah, that's it. And then from there, it's either pointing up or pointing down. Which is it?
Oh.
Yep, absolutely. Nice and quick. Now for us, we care about doing the exact area bound between x equals 0 and x equals 1, which means from here to, let's say, here. So what it's just told us to do is find all of this in here. Any thoughts on how we could do that?
Not really.
Not really, that's fine. Whenever you're doing area under a curve in any circumstance, it's always definite integral. So in this case, it's from 0 to 1, which is why we're going to do 0 and 1 on our definite integral. Otherwise, yeah, now it's just become quite simply just do that definite integral. The only time it'll ever change is when you have both positive and negative area. That's when you'll have to sort of flip things around. Do you want to finish this part off yourself or still go through it live?
We can skip it.
Skip, okay, yeah, skip it, sure. Okay, next one up is x cubed minus 8. Y equals x cubed minus 8. And then we want to do it between 2 and 4. So again, first things first, we want to get a sketch going. What's that going to look like?
There would be a y in at -8.
Yep, that's good. What else can we get?
We could get the x-intercept.
How do we get x-intercept?
Y equals 0.
That's it. 0 equals x cubed minus 8. 8 equals x cubed. X equals 2.
Yeah.
Sweet. What else?
And now we just draw like a curve going through both of them.
Yep. So key thing to identify is this is also an inflection point, so it's got a sort of wobble at that spot. But otherwise, yeah. Now, if we're told to find area from 2 to 4, what does that mean? Like specifically x, 2 to 4.
Is that the domain?
It is the domain, yeah.
Would be subforeign?
Depends on what you mean by that.
Like subforeign to the equation, and then
That would get a y value for it. What I'll say is I'll go back a step. This was the same thing as when we had like between 0 and 1. So what do we do here, and how can we repurpose that for the next question?
do we do it integral?
Yeah,
with those values?
integral of those values. Yeah, because you can see from 2 to 4, and now obviously 4 will be over here, and so we can't really see the upper bound of that, but it's all positive area. It's all above the x-axis, so nothing else is too crazy. We're now just doing integral of our function from 2 to 4, which you obviously know how to do those.
Yeah.
Cool. That's that one. Next up, we've got 4 minus x equals 4 minus x, and we're doing it from, I'm assuming 0 to 6 is where it's going to actually flip, so we'll say 0 to 6 so we can test that. That's our domain there. Now linear, I mean, that's just sort of whatever. I'll just put it down. Missed it, but I'm sure you get the point. And then we'll say 6 is here. So if you want to do area from 0 to 6 now, it's a little bit different. What's going on here?
Would we have to find between 0 and 4 first?
Yeah, so 0 and 4 gives you this section. That's good. So how do we find area between 0 and 4?
We would do integral, and then 4, 0.
Yep. That's good. So that's going to be part of it, absolutely. What about this? What's left over that we got to do?
Would we do an integral of 6 and 4?
6 and 4, yeah. Now, a couple things you could do here. How do I actually write this second integral to make it all add up properly?
Would we add the first integral and the second integral together?
You can, yep. Now, if you're putting a plus sign here, it does mean you have to change something else a little bit here, because remember, when it's below the x-axis, you have negative area. So if we do put a plus sign, what do we have to do here to make this negative into a positive?
I'm not sure.
That's okay. So I'll pause that for a second and just say, maybe if you don't remember that one, do you know another way of compensating for this negative area? How we can flip it to positive area?
Not really.
Not really? Okay. So there's two main ways. First is if you want to keep the pluses, that's fine. It just means instead of doing 4 and 6, you now do 6 and 4. You flip the order. And the reason why is because when you do your definite integrals, instead of doing capital F of 6 minus capital F of 4, you're flipping the order of the subtraction, thus going from positive to negative. That's one way of doing it. You just flip and you put the smaller number on top, bigger number on bottom. The other way of doing it, so I'll actually just write it out again. So I have 4, 0, of function. The other way is just put a minus sign out the front of it. If you put a minus sign on it, that's the same thing as multiplying by -1. And so for that reason, you change whatever the negative number would have been to an equivalent positive number. Okay?
Yeah.
Yeah. And otherwise, yeah, it just means you now got two definite integrals to solve this one and this one, or this one and this one. Either way. Fair enough?
Yeah.
Sweet. Okay, let's see. What else have we got? We can do more of the sketching ones, although might be worth now pulling up. Oh, they don't actually have that many pictures, do they? That's fine. We'll do some more of the sketching ones then. So let's go 2a, which is y equals x squared minus 2x. And we want to do that. So specifically it says find exact area bound by the x-axis and the graph. So we don't get a domain necessarily. We're just told where does the curve and the x-axis share a common area. So first up, of course, we want to sketch to see what's going on. How do we sketch this?
Could we take the x out common?
Yep, that's what I would do. X bracket x minus 2.
Would it just be a parabola?
It will be a parabola. Yep. How does this help us? It does, but how does it help us?
I'm not sure.
Not sure. That's fine. So the purpose of factorizing is to make use of the null factor law on here. So any factorized quadratic or any factorized polynomial, for that matter, basically tells you where the x-intercepts of the function are going to be. This tells us x equals 0, and this one tells us x equals 2. Because, if you set y equals 0, that gives you x-intercepts. Cool with that?
Yeah.
Now that we know where our x-intercepts are, and technically also our y-intercept, what else do we need to know to finish up the quadratic?
The y-int?
Yeah, so we kind of already have that.
Oh, yeah.
Whenever you have
The
0.
turning point?
Yeah, turning point. Where's that going to be? At least x specifically.
Would it be at 1?
It will be at 1, yeah. Any quadratic and only quadratics, they share a turning point in the center of those two things, of the two x-intercepts. Any other polynomial, it's slightly lopsided, so we can't use that all the time, but we can absolutely use it with quadratics. Only question now is, does the y value, we don't need to know exactly the y value, we just need to know, is it above or below the x-axis?
Is it below?
Below is correct, yeah. If it's a positive quadratic, then it has to shoot upwards like this, so it has to be below. That's at least how I think about it. Alternatively, if you're stressed on the day, you can just sub in x equals 1 into any of these, and if you get a negative number, you know to put it below. But okay, so now that we have our picture, it's probably a bit clearer to see what it means by area bound by curve and x-axis. It just means that the curve and the x-axis form the perimeter of the shape. So with that in mind, well, what do you think that means the area is? What area do you think is being talked about?
Would it be the one between 0 and 2?
0 and 2, yeah. Because if you think about like bound between curve and x-axis, this part is the curve, this part is the x-axis, they form the perimeter of this shape. And so, with that in mind, how do we find that area, given that it does say to find the exact area bound by it?
I'm not sure.
Not sure? Okay. How do we normally find area under any curve?
The integral?
Yep. So integral is a good start. What would the terminals of the integral be?
2 and 0?
2 and 0. Yep. And now this area, positive or negative right now?
It's negative.
Okay. Do we want it to be negative?
No.
Correct. So there's a couple of ways we could change it. How do you make it not negative?
We do what we did last time.
Yep. Which was
Wasn't it um like subbing it in like the 6 and the 4?
yeah, yeah. What's
Or
the
like switching them.
yeah? So you can switch them. That's one way of doing it. You leave it as a plus at the front, and you switch the terminals. So we can do a 2 here and a 0 here instead. The alternative is to put a negative sign at the front, because when you multiply it by -1, you flip it to being positive. So these two things are going to end up being the same. Whether you do this way or do this way, same deal. Cool with that?
Yeah.
Sweet. Okay, next up, we've got very similar thing, quadratic again. Y equals 4 minus x, and then 3 minus x. And it's the exact same thing. We're bound by x-axis specifically. So, how do we sketch?
Could we use it to find the x-intercepts?
Sure can. Yeah. Null factor law to get x-intercepts is correct. Can you see what those are going to be?
Would it be -4 and -3?
Almost.
Oh no,
Do
4 and 3?
Yeah, 4 and 3. That's it. When they have them back to front, it's a bit weirder. So it can pay off to literally write 4 minus x equals 0, and therefore x equals 4. But yes, 3 and 4 are going to be what we want. What else do we need? Not much else, really.
Yeah.
We just need to know, is this a positive or negative parabola? Is it going to point up or point down?
Mm,
You can expand it out. You don't have to guess. One of the quick ways of doing it is just expand it out real quick. Do you have a positive x squared or a negative x squared?
yeah, that's what I was trying to do.
Oh, okay.
Would it be positive?
It is positive. Yeah, correct. And if you're looking for maybe an even slightly faster way of doing that, you can actually just count the number of negative and positive x's in your scenario. So in this case, you have 2 negative x's. Negative, negative makes positive, therefore positive. Reason why I highlight that is because if you start having like squares and cubes on these things, it's now like, okay, I've got 3 negative x's here and 2 negative x's here. That's a total of 5 negative x's. Since it's an odd number, it stays as negative. It's a nice little hack, so you don't have to expand the whole thing out when you have those. But yes, so basically the exact same scenario as before. We don't even really care about we don't really care about like y information other than the overall shape. We just care about like the shape and then what the area looks like. So once again, we're bound by the x-axis, which means what's the area going to look like?
Integral.
Yep, integral.
Uh, can we just like change it now and go 3 and 4
Yep, so does the 3 go on top or bottom?
on top?
On top, yeah, that's it. 3 and 4, and then the whole function. That's it, yeah, and what you're doing is finding that little area in there. Nice. I will get you to do both ways though, because in an actual exam, one of the things they'll do is they'll go on a multi-choice and they'll say, here's a nasty area equation or like picture of an area equation. Figure out which of these multis makes it work. Sometimes I'll throw negatives in there. Sometimes I'll throw different terminals in there. So if you were to do the other way of solving that, what would the other way be?
The 4 on top.
4 on top, yep. And what do you have to do to make this work now?
Have the minus in front.
Have the minus. Yeah, that's it. Nice. Both of those are good. Okay. What else have we got? It's a whole bunch of quadratics there. Let's try something else. We'll do that cubic part F. I equals x cubed minus 6x squared. And once again, we're doing x-axis. All right. What's good here?
Could we use null factor law in this one as well?
Yeah, absolutely we can. So how are we going to make use of that?
We can find that would it be x squared bracket x minus 6?
Sure would. Yeah, that's good. So what does that tell you?
That there's a x-intercept at 6?
Yep, x-intercept at 6 is correct. It tells you something else as well.
Turning points at 0?
Turning points at 0. Yeah, super specific. That's good. So that gives you everything that will plot on this axis, at least as far as like cuts and turning points. And the question now is, how do we start the curve? Is it start bottom left or start top left?
Would it be bottom?
Bottom left, yeah. Why is that?
Because it's positive, so it has to start from the end.
Yeah, that's good. Got an x squared, got an x, they together make a positive x cubed. And so for that reason, you now get this instead. Which, yeah, that's that. So now if we're looking at curve and x-axes, how do we grab that?
Wait, sorry, what was the question?
So if we're trying to do area bound between curve and x-axes, what does that now look like?
Would we do an integral 6, 0?
Yep. So which one is 6 on top or on bottom?
Depends on what way we're going.
Well, we'll do both of them, so.
Alright. We can go 6 on top and then 0.
Yep.
And then the inside value and then put a minus in front of the integral.
Yep, that's one way.
And then the other way would be 0 on top and then 6 on the bottom.
Yep. That's it. Nice. Doing a lot of these down here, aren't they? What I'm going to do is I'm going to change this up a little bit, just so we can have one that we have to think about a little bit harder. So let's get rid of. I could have just scrolled down, but I guess I'm just going to kill it. Why not? I'm going to make up my own one. It's going to look like, well, better than that, hopefully. Okay. This is going to be 3. That's got to cross at 0. That's going to be -2. It's just some y, some cubic y. We don't really need to care what it is. The question becomes, how do I get exactly the same thing again? So we care about x-axis. How do I get this one?
Could we calculate the -2 and then 0, 1?
Yep, that's it. So what does that look like?
So the integral would be 0 on top
Mhm.
and then -2.
Yep, that's good. So that's going to be that first part.
Yeah.
Nice. What else?
And then would we find 3 and 0, 1?
That's it. We'll do both ways on that again. So
All right, so 3 on top and 0,
3 on top, 0 on bottom,
and then have the negative out,
add the negative out. Yep.
and
4.
then 0 on top, 3.
That's it. Nice. Feeling better about this stuff now?
Yeah, much better.
Yeah. Seems like you got the hang of it pretty much as far as. Like, if you can do these, this is about as hard as the book will do, I believe. Actually, no, that's a lie. I do remember one that was a little bit tougher. If you take a look at the screen share again, you'll notice question 9 has a bit of a special way of going about it. Oh, even 12 has one as well. Yeah, okay. Now we can start stepping it up a bit. So question 9, you'll notice that the area is, well, it's less about the area, more so about the function, how it's now a y² function. Have a think about what's going on there. I don't expect you to get it because it's not really taught, nor does it really show up in a exam scenario. But have a think about it either way. Or I guess really the question I'll pose to you is, why does this find that area? What is it about this that works?
I'm not sure.
Yeah, that's fine. So the similarities that I would highlight would be, if you compare the two functions, you'll notice it's kind of similar, right? Like you got this y² in here. If you were to make this function look like this function, any thoughts on what you would do? You can see they got very similar terms.
For the first equation, I would square root both sides.
Yes, that would get y on its own, but that
Yeah.
won't really make it look like this in part B. If you
Mm-mm.
had to make it look like what's in part B, what would you do instead?
Or I would divide the 9 from that side and have y² over 9.
Yeah, that's a great start. So you're going to have y² over 9 equals 1 minus x. It's pretty close. What else could we do to get it closer?
Uh, we could move the 1.
Yep, move the 1. Y² over 9 minus 1 equals minus x. It's pretty close. We're almost there.
Um, and then could we divide it by -1?
Divided by -1, correct. So final answer, x equals 1 minus y² on 9, which is exactly what appears in the integral. And so the lesson here is, if you have a relation that is, well, let's try to draw better axes than that. If you have a relation that is otherwise really tough to anti-diff, what you can do instead is rearrange that thing for x and then anti-diff it with respect to y. That will also get you area, but this time the area is considered with respect to the x-axis, the y-axis, not the x-axis. Cool.
Yep.
And so basically what you need to know is, what are these values now, since that's your new thing that you're looking for. And so for that, well, that just means you're subbing in x equals 0 into this. 0 equals, well, maybe not even to that. Maybe sub it into the original y squared thing. That'd be a little bit easier to rearrange for. But basically, that's going to give you some value there, and then your integral is therefore going to be from, let's say it's 0 to 2, but you're doing it for this. Okay?
Yep.
Cool. There is one other thing I want to show you. Question 12 only reminded me of it. Probably a simpler way of talking about it will be to show just a basic natural log thing. So the idea is that you have a natural log graph, it cuts through something here, and you want to figure out like area bound here. So let's say this is just regular old natural log x. So natural log of x, y equals 0, e to the 0, so that's 1. And then let's say this is just 3, because whatever. First question, and it's going to be a bit of a trick question for you. How do you find this area?
Could we do integral 3 to 1?
Yep, integral 3 to 1 of the natural log. That would be cool. Only one problem. No idea how to antidiff a log. If you take a look at the screen share again and you look at the table of known integrals, you'll notice that log only ever appears on the right-hand side of the table, not the left-hand side, which is what we want. So antidiff of natural log is not something we know how to actually do. Or at least we're not given the formula for doing so. So here's a technique that you use to handle this situation. The situation comes up enough to where I think it's worth exploring, by the way, which is why I'm having a look at it. And so what you would do is you rely on the symmetry of the inverse. So if you remember, inverse just means flipping along the line y equals x, which means that if you were to find the inverse function, it would look something like this, where this would be now y equals 1, and this would now be like y equals 3. I know I haven't drawn that super well, but these are supposed to be the same area. If you were perfectly symmetrical, this would be the same area as this one here. Cool so far?
Yep.
Okay, now from there, do you remember how to do the inverse of a log?
Yeah.
What's that all about?
So we'll change the y to x, so it'd be x equals y, and then we would go on the x side, e to the power of x equals y.
That's it. Yeah. So this is just your e to the x. Now, fun part is we can solve this area now because we can antidiff an e to the x. The problem, a little bit of a problem, is that all of our stuff is vertical. We need something horizontal because if we try to do the thing that I talked about earlier, where you do your antidiff with respect to y, you're going to get back to this scenario here, which is not what you want. So we need to do a thing that's slightly different. So if we want to grab this area, I haven't really talked about it today yet. Have you done area bound between two curves yet?
I don't think so.
Okay. So like if I gave you a quick graph and it was like, you got this here, and then you've got this here, and you're told to find this area. Nothing like that before?
No.
Okay, that's fine. So I'll walk you through it. First things first, you want to get a horizontal distance going. So you know this is 0. This bound area stretches horizontally up until here, right? So if you want to figure out the horizontal distance, how do you get this endpoint here?
Would we do it by solving one of them?
By solving one of them? Yep. So that is correct. What solve are we doing? What's special about this point?
That it kind of intersects?
Yeah, intersects. Intersects 3. So what does that mean? How do we solve that?
Uh, would we go integral 3, 1?
Not quite integrals here. So if we're looking for just intersection, that's when we're doing just regular solve. Right, so you're basically looking for, if you want to get the x value at this spot, this just means the intersect between y equals 3 and y equals e to the x. So you just mean e to the x equals 3, and therefore x equals the natural log of 3. That's all that is. Just do a quick equation. Cool?
Yeah.
Okay, so we know it ends at natural log 3. That gives us the terminals of our integral, because you need to do horizontally, not vertically. And so when we're doing our integral, we're now doing from 0 to natural log 3. That's one part of it. Now, if we just do from 0 to natural log 3, we would be finding all of this, not all of that. So, not exactly what we want yet. There's a couple of ways we can handle this. There's two that I can think of right now. One of which uses stuff you've probably done before, one of which doesn't. So I'm curious if you think of any idea on how you might get just this part. Oh, sorry, just this part instead of this part.
Would we minus what we found if we solve the rectangle and then minus?
Yes, nice. If you get the rectangle, then you, yeah, exactly right. So rectangle's pretty chill, of course. If you know this is a height of 3, so 3 vertically, and natural log of 3 horizontally, then your, we'll call it area total, is 3 natural log 3. All right, length times width. And then the area that we don't want, we can solve pretty handily by just doing that integral. So if you chuck in your e to the x, that's going to be like a, I don't know, a b for bad. A g for good area is now just going to be the total, that, minus the bad bit. Exactly right. Yeah, got it perfectly fine. So if you like that, that's super cool. Otherwise, you can use something you'll look at later, which is doing area bound between two curves, where all you got to do is figure out what curve is on top of the area and what is on bottom of the area. In this case, e to the x is the bottom one and 3 is the top one. And so all that means is when you do your bound area, you still keep it over same domain. You start with the top curve and you subtract the bottom curve. This is the exact same thing as that procedure. So obviously, quicker way of doing it, but if that's more intuitive to you, then you can use that, at least in the meantime, while you're still learning this a bit better. Cool?
Yeah.
Okay. That's described in, where is it? Applications? Yeah. That's in like the module for applications of integration. So you look at the integration by recognition stuff, which is different. And then there's this area bound between two curves here. We look at what happens when it's just one on top of the other, and you look at what happens when they cross over as well. Cool?
Yeah.
Yeah. I guess the only thing I'll say to that is it doesn't actually matter where these curves are on the axes. Like I know this is fully positive, like entirely above the x. This one's also fully above the x. It doesn't actually matter. You do the exact same procedure regardless. So if, for instance, I draw another one, let's say, and this did actually come up, so I'm going to see if I can draw it well. So let's see, I think it was something like that, and then try to draw the reflection of it. or something like that, and they say find all this bound area in here, and you can see it's kind of all over the shop, right? It's some is below, some is above. It doesn't actually matter. The only thing that matters is in each of these individual sections, which line is above the other, not where is it with respect to the x-axis. So in this case, you're doing integral of red minus green for this section. Then you're doing the integral of green minus red for the second, because that's the top and that's the bottom. And then you double this one up again for the second bit. So red minus green. Okay?
Yep.
Sweet. That's pretty much it there. So if you want me to answer any final questions, feel free to let me know. Otherwise, I'll leave you to it.
All right. Thank you so much.
Take care. Bye.
You too. Bye.